Hey guys, chapter 10, hypothesis testing regarding a parameter. And we're going to start with 10.1, so the language of hypothesis testing. So a friend of yours wants to play a simple coin flip game. If the coin comes up heads, you win. If it comes up tails, your friend wins. Suppose the outcome of 5 plays of game is tail, 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 tail. Is your friend cheating? So we will determine the probability of getting 5 tails in a row, assuming that a coin flip is fair. So the flips of a coin are independent. So the probability of 5 tails in the row is equal to the probability of tails and tails and tails and tails. So that would be probability, because these are all independent events. Probability of tails is 1/2, and we have 5 copies of those, so we could jump straight to this and get this value right here. So there's a 3% chance that this would happen. Now, if we flipped a fair coin 5 times, 100 different times, we would expect about 3 of those 100 experiments to result in all tails. So what we observed is possible, but not likely. So you can make one of 2 conclusions. Either 1, your friend is not cheating and happens to be lucky. Or 2, your friend is not using a fair coin. That is, the probability of obtaining a tails on one flip is greater than 1/2. And therefore he is cheating. So is your friend cheating, or do you just happen to experience an unusual result from a fair coin? So this is a heart of hypothesis testing. We make an assumption about reality. In this case, the probability of obtaining heads is 1/2. So we then look at or gather sample evidence to determine whether it contradicts any assumption. And that leads us to the definition of hypothesis. So hypothesis is a statement regarding a characteristic of one or more populations. In this chapter, we look at hypothesis regarding a single population parameter. Hypothesis testing is a procedure based on sample evidence and probability used to test statements regarding a characteristic of one or more populations. So steps in hypothesis testing. 1, we make a statement regarding the nature of the population. 2, we collect evidence to test the statement. 3, analyze the data to assess the plausibility of the statement. The null hypothesis. So the null hypothesis denoted H sub O or H naught. There's a couple of different ways to say this right here. Well, this book is going to call it H naught. So H naught is a statement to be tested. The null hypothesis is a statement of no change, no effect, or no difference, and is assumed true until evidence indicates otherwise. The alternative hypothesis denoted H1. Sometimes denoted HA. In this case, it's going to be H1. So this is a statement that we are trying to find evidence to support. In this chapter, there are 3 ways to set up the null and alternative hypothesis. So we could either have the parameter equal something. So for all of them, H naught is going to be equal to. So notice equal to here, equal to here, equal to here. But the difference is with how they state it. So the alternative could either be not equal to, it could be less than, or it could be greater than. So these are 3 different tests. So notice here, we are not equal to. So what we could say is, what they called this was a 2-tail test. But what we could say is not equal to means that we're looking for the data to be in the middle. So if it's in the rejection regions of the left side and the right side, then we don't accept it. This one over here, this is considered a left tail test because this arrow here is pointing in this direction, in the left direction. So what we're expecting is for majority of our data to be greater than that value or less than that value. So if it's too small, then we're going to reject it. versus this one, our alternative hypothesis is pointing in the opposite direction. So this is pointing in the right direction. So we're going to have a right tail test with this one. So those are our three different assumptions: two-tail test, a left tail test, and a right tail test. But we all base it off of the way that we set up the null hypothesis and the alternatives. So H naught and H1. So in other words, the hypothesis is a statement of status quo or no difference and always contains a statement of equality. So there's always going to be an equal sign in the null hypothesis. So it's going to be some sort of parameter equal to some other parameter. H1 is going to have still the same thing, but this one could either be not equal to, less than, or greater than. So left and right tail tests are referred to as a one tail test. Notice in the left tail, the direction, and in the right tail, the direction is the opposite direction. So it points to the right, points to the left. In all three tests, the null hypothesis contains a statement of equality. So it's always equal to for the null hypothesis. So determine the null and alternative hypotheses, state whether the test is two-tail, left tail, or right tail. A Medco pharmaceutical company has developed a new antibiotic for children. 2% of children taking competing antibiotics experience headaches as a side effect. The researcher for the FDA, Food and Drug Administration, wishes to know if the percentage of children taking the new antibiotic who experience headaches as a side effect is more than 2%. All right, so we have H naught, we have H1. So here, rereading everything, first thing I want to know is what our parameter is. So the parameter could be one of three things. It could be the mean, it could be the standard deviation, or it could be the proportion. Okay, so the medical pharmaceutical company has just developed a new antibiotic for children. 2% of children taking the competing antibiotics experience headaches. Researcher wishes to know the percentage. So percentage tells us that we're dealing with the proportion. So our parameter is going to be proportion. And now we know for sure this one's going to be equal to. So now we have three options for this one here for our alternative. And a researcher from the Drug and Food, or the Food and Drug Administration, wishes to know if the percentage of children taking the new antibiotic who experience headaches as a side effect is more than 2%. So the number here is going to be 2%. 2% here as well. And here, more than 2%. So more than 2% is going to be greater than. And from here, since it's greater than, what we would do is this, our inequality is pointing to the right side. So it's going to be a right tail test. And there we go. Let's see if we missed anything. So 2%, so they use something a little bit different. They use 0.02. They use the actual decimal percentage or decimal point. I use a percentage. Either way, it's still gonna look the same. And here we go. So H naught, the proportion of individuals taking the new drugs who experience headaches as a side effect is 0.02, so equal to 0.02. Or the proportion of individuals taking the new drug who experience a headache as a side effect is more than 0.02. More than causes the greater than symbol. And because of that, so right tail test, because alternative hypothesis is pointing to the right. Next, the Blue Book prize of a used 3-year-old Chevy Corvette is 59,083. Grant wonders if the mean price of a used 3-year-old Chevy Corvette in Miami metropolitan area is different from 59,000. Okay. So we have our null hypothesis, we have our alternative. And here our parameter, Grant wonders if the mean, so that tells us that we're going to be using mean. Null always has the equal sign. And from here, we're going to go to the price. So the mean price, 59,083. And here, Grant wonders if the mean price, blah, 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 is different from. So is different from, our three options are going to be not equal to, less than, or greater than. So he doesn't mention less than or greater than or anything of that sort. So it's going to end up being our not equal to part. So our null hypothesis is going to have not equal to 59,083. And now because of this, we don't have any direction. We're not less than or greater than. So because this is not equal to, this tells us that it's a two-tail test. And perfect. Lastly, not lastly. So the hypothesis deals with the population mean. So that's why we used mean. So if the mean price of a 3-year-old Chevy Corvette in Miami is no different from the blue price, and the population mean in Miami will be 59,083. So this statement of no difference, Grant wants to know, this is a statement of no difference. Grant wants to know if the mean price is different from this. This supports a statement that we're attempting to find the evidence to support. So here, what we're doing is, just like I showed earlier, we have the mean equal to 59,083 and not equal to. So is it different or is it not different? So again, we weren't shown anything about greater than or less than or anything. So we would use this part right here. And because it's not equal to in our alternative, because it's not equal to, then we're using our two-tailed test. Next, the standard deviation of contents. Well, they already start off with that. So let's go ahead and start writing H0, H1. Standard deviation. We're always going to have the equal to in this part. Okay, so the standard deviation of the contents in a 64-ounce bottle of detergent using an old filling machine is 0.23 ounces. The manufacturer wants to know if new filling machine has less variability. So less variability, we would have less than 0.23. And here we have our test. So because this is pointing to the left side, we're going to have a left tail test. And there we go. That's how we would state that. So the hypothesis deals with the population standard deviation. If the new machine is no different from the old machine, the standard deviation of the amount in the bottles filled by the new machine will be 0.23 ounces. This is a statement of no change. The company wants to know if the new machine has less variability than the old machine. This is a statement that we're attempting to find the evidence to. And here they have H0 equal to H1 less than, because they use the less than in the statement. Our parameter is standard deviation, and they give us this value right here. And because the symbol is pointing to the left, this is going to be a left tail test symbol in our alternative hypothesis. Next, we have the difference between a type 1 and a type 2 error. So there are 4 outcomes from hypothesis testing. So 1, we would reject the null hypothesis when the alternative hypothesis is true. So this decision would be correct. 2, we do not reject the null hypothesis when the null hypothesis is true. This decision would be correct as well. 3, we would reject the null hypothesis when the null hypothesis is true. This decision would be incorrect. So this type of error would be called a type 1 error. And we do not reject the null hypothesis when the alternative hypothesis is true. So this would be a type 2 error. So again, shown in this way, we either have the null hypothesis is true or the alternative is true. So if the null hypothesis is true and we do not reject the null hypothesis, then we're good. Nothing bad happened, or we're concluding the correct thing. If the null hypothesis is true and we do reject the null hypothesis, then we would have a type 1 error because we should not have rejected this one. And now the opposite. So for the alternative being true, if we do not reject the null hypothesis, then we would have a type 2 error. So remember, if we do not reject the null hypothesis and we should have rejected the null hypothesis, that would result in a type 2 error. If we reject the null hypothesis and the alternative was true, then we have the correct conclusion. So nothing bad would happen here either. But we have 2 separate errors that we would have to take a look at. So let's look at the difference in errors. So the Medco pharmaceutical company has just developed a new antibiotic. 2% of children taking competing antibiotic experience headaches as a side effect. A researcher from the FDA wishes to know if the percentage of children taking the new antibiotic who experience a headache as a side effect is more than 2%. So the researcher conducts a hypothesis test. We have H naught, we have H1. So H naught was the P equaling 0.02. H naught was, or H1 was P being greater than 0.02. So explain what it would mean to be a type 1 error. So remember, a type 1 error is that the null hypothesis is true and we reject the null hypothesis. Let's see what would happen. So if we're rejecting the null hypothesis, if we're not ever saying that this is incorrect, what we're actually saying is, so a type 1 error is made if the sample evidence leads the researchers to believe that the percentage of people is greater than 0.02. So that is, we reject the null hypothesis when in fact the proportion of children who experience a headache is not greater than 0.02. So this is a little bad, not too bad, because if we're thinking that it's greater than, then we might shut this medication down. However, with the type 2 error is made if the researcher does not reject the null hypothesis that the proportion of children experiencing a headache is equal to 0.02, when in fact the proportion of children who experience a headache is more than 0.02. So in other words, the sample evidence led the researcher to believe that P is equal to 0.02, when in fact the true proportion is a value much greater. So this one would actually result in something that's a little bit worse. So if we're thinking that it's 0.02 when in fact it's greater, thinking that it's 0.02 would possibly just lead us to believe that it's not that bad. And we're going to keep this drug on the shelves for kids to continuously get headaches with, when in fact the number is much greater than 0.02. So 0.02, like this is going to end up making a lot of kids sick. So we don't want that to happen. And I'm kind of exaggerating the point here, but I'm just imagining a bunch of little babies having headaches, and that's not something that we want. That's not something that we should strive for. So because of that, we're going to consider these 2 things here. So alpha is going to be the probability of a type 1 error. So remember, probability of rejecting the null hypothesis when the null hypothesis is true. So that's where we're going to get this alpha and this beta. Beta is going to be equal to a type 2 error, not rejecting the null hypothesis when the alternative is true. So because of that, what we're going to end up doing is rejecting, like if we have enough evidence, we are going to reject the null hypothesis and accept the alternative. And that's going to alleviate a lot of these problems. And we will only have an alpha size probability that those end up true. The level of significance alpha is a probability of making a type 1 error. So as the probability of a type 1 error increases, the probability of a type 2 error decreases, and vice versa. So A, state the conclusions to hypothesis testing. So caution, we never accept the null hypothesis. So never accept the null hypothesis, because without having access to the entire population, we don't know the exact value of the parameter stated in the null hypothesis. Rather, we say that we do not reject the null hypothesis. This is like the court system never declare a defendant innocent, but rather say that defendant is not guilty. So not, just kind of think of that. So innocent until proven guilty, but in reality, it's just not guilty. It's not that they're innocent right now. All right. So the Medco pharmaceutical company has just developed a new antibiotic. 2% of children taking the medication or taking competing antibiotics experience a headache as a side effect. A researcher for the FDA believes that the proportion of children taking the new antibiotic who experience a headache as a side effect is more than 2% or 0.02 from a previous example. We know the null hypothesis to be P equals 0.02, the alternative to be P greater than 0.02. A, the null hypothesis. So suppose the sample evidence indicates that the null hypothesis is rejected. So state your conclusion. So in this case, remember what we're looking at is H naught P is equal to 0.02. H1 P is, what's it, less than or greater than? Ooh, opposite. Is greater than 0.02. So again, what we did is we rejected the null hypothesis. So rejected the null hypothesis and accept the alternative. So with this, we're stating that the proportion of children experiencing headaches after this medication is greater than 2%. So that's the way that we're going to state it here. So the statement in alternative hypothesis is that the proportion of children taking the new antibiotic who experience a headache as a side effect is more than 0.02 because the null hypothesis is rejected. There is sufficient evidence to conclude the proportion of children who experience a headache as a side effect is more than 0.02. So that's just the way we would say that we would state the null hypothesis. So suppose the evidence indicates that the null hypothesis is rejected, state the conclusion. So here we're not accepting the alternative hypothesis, or we're not accepting the null hypothesis. We're just stating that we don't have enough evidence. So here, remember, we're not ever going to accept the null hypothesis because we don't have the entire population, or we don't have access to the entire population. But instead, what we're going to say is that we do not have enough evidence at this moment. So because the null hypothesis is not rejected, there is not sufficient evidence to say the proportion of children who experience a headache as a side effect is more than 0.02. And one more time, just so we're clear, we have H naught and H1. This one is always going to be our parameter equal to some other version. This one is always going to be our parameter. It's either going to be not equal to, which is a two-tailed test, less than, which is a left-tailed test, or greater than, which is a right-tailed test. The next thing is we're never going to accept the null hypothesis. We will only accept the null We'll only accept the alternative if we reject the null hypothesis. So our goal here is always to reject the null hypothesis. So reject the null. So reject the null hypothesis, so that way we could accept the alternative. Rejecting null hypothesis, we get to accept the alternative. Otherwise, we don't have enough evidence to support either one of our claims. And that wraps up 10.1. If you guys have any questions, go ahead and email me, but if not, good luck.